Okay, guys, so I'm recording this lecture on December, let's see, I think it's the 8th. And we're basically, the lecture is on completing our discussions on Maxwell's equations. So I think last time we talked about these are, I gave you guys Maxwell's equations, including the actual part that Maxwell, his contribution to the equations to complete Ampere's law and make these equations complete. So this lecture, I'm going to talk about what the sort of the thinking was, or how do we derive that, and how was there, why was there a need for this? So let's first look at the state of E&M equations before Maxwell. So E&M equations before Maxwell. So we had Faraday's law, which said, which is the curl of the electric field was the change of the magnetic field with respect to time. So this was Faraday's law. Then there was the curl of the magnetic flux is equal to the current density. So this was Ampere's law. And basically this says that if there is a current flowing through a wire, then you would have this sort of magnetic fields going around. And if you have a closed loop, then basically inside this, so remember that the curl equation is talking about as if you had like a lasso. So you're taking a line integral around a closed surface. That's the meaning of this curl, if you want to visualize that. So let's say I had a lasso that went around this section, say. So I was integrating around this section. There's no current here, so this del cross H would be 0 here, if I look at it there. But if I took my section around sort of this area where there is a current flow, I'd be going around this way, then this line integral would include this current. So in this area, so here, the curl of H, here the curl of H would give me the current over the area. This is the current density. And here, this would give me del cross H. This would be 0 over here. Okay, and then we had the divergence equations on the other hand. So this is like the curl of the electric field is the rate of change of the magnetic field. The curl of the magnetic flux, I guess, is equal to the current density. And then we have the divergence equations. So divergence of the electric flux is the charge density in a volume, and the divergence of the magnetic field is equal to 0. So together, these were Gauss's laws. And just making another few points here, the reason for this is that there is no isolated magnetic charge. So remember that these divergence type equation is more like a volume integral. So you're taking a volume. So these are like line integrals, like a lasso grabbing onto something. These are like a volume integral, like you're sort of closing your fist onto a volume and seeing what's inside. So here the electric flux, there's actual, there is such a thing as an isolated electric charge. So if you take a sphere, it is possible that at some points, as long as there is an electric charge inside your sphere, you would get some value. But in fact, the magnetic charge, you would not get there's no such thing. So you'd never end up with that. Okay, so then you would, the last thing then, so you'd have these four equations, and the last thing is that you'd have along with these is the charge conservation, which is that the divergence of the current density is equal to the change of the charge density with respect to time. And that means that, if you have a charge density somewhere, and if you looked at, the current leaving, if you had a surface around, or a volume, so this is again a volume, so this is del dot J is a volume. So if you had a volume and you noticed current coming out of this thing, the total current coming out of this thing would have to equal to the change in the charge density inside. So this is some surface S0, and this would be sort of the current coming out in any particular location. So this is what was the state of understanding of electromagnetics before Maxwell. So everything was sort of made sense, except there was one thing that didn't, which was in this Ampere's law. In this Ampere's law, there was an issue here. Because there was an inconsistency in this Ampere's law between this law and charge conservation. So let's see why. Okay, so again, so if I take this Ampere's law, so let me grab this thing, copy it over. So if I had this, and let's say I took the, what if I take the divergence of both sides? It's like a permitted function. If I did that, so if I take the divergence of a curl on the left side, as we'd seen before, this results always in this always equals to, so this operation of taking the divergence of a curl would always gives a zero result. Give zero result. So on the left-hand side of this equation, we'd have 0. All right, but this divergence of J isn't always guaranteed to give 0. In fact, the conservation of charge equation says if there is charge inside this volume that we're looking at, this would be non-zero because of charge conservation. This could be non-zero. So going back to that. So this could be non-zero. So we got a problem here with Ampere law. So there's a inconsistency, I'm sorry, an inconsistency between Ampere's law and charge conservation. Okay, so what do we do with this? Well, let's start by looking at how we need. So basically, there's a problem here. Charge conservation is something that's been around for a long time, and it's pretty accepted as a sort of a physical law. So